Good morning and welcome you all to this session on fluid machines. In the last class, we discussed the axial flow and radial flow machines depending upon the direction of flow. And next, we discussed the impulse and reaction machines. Now, today we will discuss mainly the principle of similarity applied to fluid machines. But before that, we will just see how the efficiencies of fluid machines are defined. As I have already told and you have seen that fluid machine is a device which converts stored mechanical energy, a stored energy in the fluid into mechanical energy and vice versa. The efficiency accordingly of a fluid machine is defined as the ratio of output energy divided by input energy. Now, output energy may be mechanical energy delivered by the machine or the energy stored in the fluid depending upon whether it is turbine or pump. Similarly, the input energy will be mechanical energy or the stored energy in the fluid or the mechanical energy depending upon it is turbine or pump. And in this connection, two efficiencies are defined. One is hydraulic efficiency concerning the energy transfer between the fluid and the rotor, and another one is overall efficiency concerning with the energy transfer between the fluid and the shaft. Now, the difference in energy at the rotor and at the output shaft is the energy absorbed by glands, bearings and other couplings due to friction. Now, if we see that in detail, let us write this. There are two efficiencies. One is hydraulic efficiency. One is hydraulic efficiency, which is given by eta H, which deals with the energy transfer between the fluid and the rotor. Another is overall efficiency. Overall efficiency eta O, which is concerned with the energy transfer between the fluid and the output shaft. Now, let us define separately for turbines. Hydraulic efficiency is defined as the output energy of the turbine. What is this? This is the mechanical energy delivered by the rotor. That is mechanical energy delivered by the rotor. Mechanical energy delivered by the rotor. Mechanical energy delivered by the rotor divided by the in the denominator is energy, that is the stored energy of fluid at inlet to rotor or the machine, fluid machines. This energy of fluid at inlet is the available energy, stored energy, from which the conversion takes place in the rotor, and rotor delivers mechanical energy in the form of its rotation. Now, here this energy available to the rotor at the inlet to the rotor and machine is same, since the stator is fixed member, so does not move. So, there is no mechanical energy transferred. So, therefore, if we neglect the heat loss from the machine and the viscous dissipation, the mechanical energy at inlet to the machine and mechanical energy at inlet to the rotor remains same. This is because stator remains fixed. Now, if you think of not mechanical energy, the total energy inclusive of intermolecular energy also, which we call as thermal energy, then if we neglect the heat loss from the machine or no heat transfer between the machine and the surrounding, so by the conservation of energy, energy at inlet to the stator, or this the inlet to the machine, will remain as the inlet to the rotor, because stator does not perform any mechanical work. So, therefore, we write energy of fluid at inlet to rotor or machine. The overall efficiency is now the denominator remains same, this is the input energy, energy of fluid, same thing, energy of fluid at inlet to machine or rotor, whatever you write, and this thing is the mechanical energy in output shaft at coupling, and the difference between the two is the friction in glands, bearings and couplings. And if we now divide this overall efficiency by the hydraulic efficiency, if you divide it, this thing is cancelled, energy of fluid at inlet. What we get? We get mechanical energy at shaft, in output shaft. I am not writing the entire sentence, and here the mechanical energy at rotor, delivered by the rotor. I am not writing at rotor. That means this becomes overall efficiency divided by the hydraulic efficiency is mechanical energy in shaft, output shaft, divided by the mechanical energy delivered by the rotor. That means mechanical energy at rotor, and this is always less than this because of the mechanical friction in glands, bearings and couplings. So, therefore, this ratio is always less than 1, and this is defined as mechanical efficiency. This is eta m, mechanical efficiency, and hence we can write the overall efficiency is hydraulic efficiency into mechanical efficiency. Okay. Now, next is similar is the case of pumps or compressor. In case of pumps and compressors, we can define similar way the hydraulic efficiency. Here output is the mechanical energy gained by the fluid, that is mechanical energy gained by the fluid at final discharge, means discharge from the machine at final discharge, and the denominator is mechanical energy supplied by the rotor. Mechanical energy supplied to the rotor or by the rotor, supplied to the rotor, out of which how much energy is gained by the fluid at final discharge. That is the hydraulic efficiency. That takes care of the losses in the fluid flow. Similar is the case of turbine. So, this is the definition of hydraulic efficiency of pumps and compressors. Now, here mechanical energy gained means this mechanical energy at the final discharge relative to its mechanical energy at inlet, because fluid at inlet has some mechanical energy. That is why mechanical energy gained by the fluid at final discharge. And in the similar way, following the similar line of thought as we discussed in case of turbines, the overall efficiency, in this case the output will remain same, mechanical energy gained by the fluid at discharge, final discharge or simply at discharge. Now, here mechanical energy supplied to the rotor, here input will be mechanical energy supplied to the shaft. That means, here the final initial input point is shaft, like the turbine the final output point is shaft. So, therefore, overall efficiency deals with this energy supplied to the shaft and the energy gained at final discharge. And in the similar way, hydraulic overall efficiency divided by the hydraulic efficiency is the mechanical efficiency, which is the ratio of what? Ratio of, if you divide this by this, is the mechanical energy supplied to the rotor divided by mechanical energy supplied to shaft. That means mechanical energy to rotor, and I am writing in short mechanical energy to shaft, input shaft. and this is always less than 1 because energy supplied to shaft is not going to the rotor because of the frictions in those elements, glands, bearing and coupling. So, rotor receives less energy. So, this is the mechanical efficiency. So, this way usually the efficiencies of the fluid machines are defined. Now, we come to a very important chapter or very important section is the principle of similarity applied to fluid machines. So, before I discuss this principle of similarity applied to fluid machines, I like to have a recapitulation or a brief review of the concept of principle of similarity in physical processes, okay, to brush up your knowledge that already you have gathered in your basic fluid mechanics course. As you know, that most of the engineering problems or the problems related to practical applications, their solutions are determined from experiments. This is because of the complex nature of the practical problems or engineering problems in practice, where besides the analytical method, even the most updated CFD tool cannot take care into consideration of all the aspects and features that happen in practice are associated with the problem. So, therefore, we always depend on experiments. Even if we do theory, these are being calibrated from the experiments. Theories are done, the CFD analysis are made to guide the experiments in which direction the experiments will go and to predict the qualitative trend. But to have a quantitative final solutions of those engineering problems, we always do the experiments and the solutions are obtained mostly from these experimental studies. Now, because of economic advantage, saving of time and ease of investigations, it is not possible in almost all instances to do the experiments in laboratory under the identical conditions in relation to the operating parameters and the geometry of the system that prevail in practice. It is not possible. So, therefore, we have to do the experiments under altered conditions that happen in practice. For examples, if we have to do an experiment to find out the pressure distributions over an aircraft wing, we have to do the studies, but where we cannot have the aerofoil of the dimensions that an actual aircraft does have. We cannot have the fluid velocities, the condition of pressure and temperature similar to that happen in practice. Similarly, for example, if we think of simulating or studying the flow through pipes, which will generate data to predict the performance of the pipe network in practice, we cannot do the experiment with such big dimensions of pipe, such big diameters of pipe, length of pipe, and sometimes we cannot have that flow rate, we cannot generate that flow rate in our laboratory. For example, to find out the drag in a ship or submarine, we do experiments. If we want to do experiments in our laboratory, we cannot have a ship or submarine of its actual dimension, and we cannot create a she in our laboratory. So, therefore, laboratory tests are always performed under altered conditions that happen in actual practice. But at the same time, the results from these tests have to be used to predict the performance of the actual system under actual operating conditions. So, now in relation to this, there are two very pertinent questions come up. One is that which ensures us that the results from these altered conditions, tests at altered conditions in the laboratory can predict the performance parameters of the actual system which are operating under different conditions in practice. How we can compare this? What has to be satisfied to make comparisons or to use these results for predictions of parameters in practice, number one. And number two question is that if a physical process depends upon a number of independent controlling parameters, then to find out the influence of each and every parameter, we have to do a number of experiments by varying each and every parameter by keeping other parameters fixed. So, which involve huge cost, huge time. Okay. Can we do this way to save time and cost that vary some less number of variables and can predict the performance parameters, the influence of the variable, other variables on the performance parameters of the system. Now, these two questions are very important, and a positive clue in answering these two questions lie in the principle of physical similarity. That means, this can be done. That means, the results from laboratory at altered conditions can be used to predict the performance of the same process in practice at different conditions, and at the same time we can reduce the number of experiments by varying only few independent controlling parameters, so that the influence of other controlling parameters can be determined from that, provided the physical similarity exists between the two problems. So, therefore, I come to this physical similarity. Now, physical similarity, the first line of understanding is that physical similarity has to be sought between two problems defined by the same physics. First of all, you have to understand that the physical similarity always, if we say that the two problems are in 100% or identical physical similarity, have physical similarity, but the problems have to be defined by the same physics. So, first requirement of physical similarity, that physical similarity has to be sought between the problems governed by the same physics. For example, the flow governed by the gravity force and inertia force, for example, a surface wave in a sea, and another process, that flow of fluid through a pipe, which is governed by inertia force, viscous force and pressure force, cannot be made similar under any identical condition. We can make similar situations of pipe flow problems at different operating conditions, or the surface wave problems relating to surface wave at different operating conditions. So, the physics of the problem has to be same, and in that case the physical similarity to be maintained or to be obtained, we have three types of similarity have to be ensured. One is geometrical similarity, one is geometrical, another is kinematic similarity, and another is dynamic similarity. Another is dynamic similarity, geometrical, kinematic and dynamic similarity. Now, geometrical similarity is the similarity of dimensions, which tells that the system dimensions in actual case and in the laboratory case should be such that the ratio of the corresponding dimensions should be same, and it is maintaining the same shape. This we know since our childhood. An example I am giving the geometrical similarity. Let us consider the two cylinders whose length is 1 L and the diameter D. If we have got another cylinder whose length is L by 2 and the diameter is D by 2, they are geometrically similar. Similarly, if we have a parallelepiped, of this A, this is B and this is C, and if we have a small parallelepiped where A, B, C are reduced by the same proportions, less this is A by 3, this is B by 3 and this is C by 3, then they are geometrically similar. Now, what is kinematic similarity? Kinematic similarity is the similarity of motions that requires that the ratio of the velocities of particular component of velocities at the different systems should be same at corresponding points. That means, the ratio of the velocities of a particular velocity, that means particular velocity component of both the system and the in the laboratory, both the system in the laboratory and that in practice should be at the same ratio at the corresponding points. Let us define this way. Let us have u, v and w, three component of velocity x, y, z. If we have a system 1, if we have a system 2 and we sought the kinematic similarity between this system, then u for system 1 divided by u for system 2, this ratio has to be same at corresponding points of the system 1 and system 2. Similarly, V of system 1 divided by V of system 2 will be same at corresponding points. Similar is the case of W, and accordingly one can write this also this is U by V of system 1 divided by U by V of system 2 at the corresponding points has to be also same for both these systems. So, therefore, you see the ratios of the corresponding velocities will be same at corresponding points between the two systems, and accordingly the ratios of any two component of velocity of system 1 and system 2 will be same at the corresponding points of the two systems. This ensures the kinematic similarity. Similarly, the dynamic similarity will ensure the similarity of forces. So, dynamic similarity is the similarity of forces. Dynamic similarity is the similarity of forces. Similarity of forces. Dynamic similarity is the similarity of forces. Similarity of forces. Now, problems, physical problems are governed, all physical problems or physical processes are governed by the different forces. Let us consider few such forces. Inertia force, I am writing in short, I am telling it inertia force, viscous force, gravity force, surface tension force, elastic force and so on. A particular problem or a particular process may not be governed by all the forces. Some processes may be governed by inertia force, viscous force, pressure force, another force is the pressure force, inertia force, viscous force, pressure force. Some may be governed by inertia force, gravity force, some may be governed by inertia force, viscous force, gravity force. So, to ensure the dynamic similarity, the ratio of the forces at the corresponding points between this system and between the two systems, system 1 and system 2, between which their similarity is sought for, has to be same. So, to make this, we have to find out the parameters that define the inertia force and viscous force. Now, here we know the ratios of velocities we get in terms of the velocities, but when we say that the ratio of inertia force by viscous force has to be same for both the systems, then we have to know that the ratio of inertia to viscous force is given by which parameters, which variables of the fluid flow. Usually we deal with the velocity, pressure, density, viscosity, the fluid property or the characteristic geometrical dimensions of the problem. So, therefore, it is customary to express these ratios of forces in terms of those variables concerned with the fluid flow problems. So, this is done by scaling the forces. So, how to done? Now, inertia force, if you scale, inertia force is equal to mass times acceleration. Acceleration. Now, what is mass? Mass can be scaled as rho into, if L is the characteristic dimension of this system, rho L cube, and acceleration is the rate of change of velocity. So, if we take the characteristic velocity as v, so acceleration is v divided by the time, and time also we can write in terms of L by v, in terms of the characteristic length and the characteristic velocity. So, that this becomes is equal to rho this L square v square. So, therefore, we see we can scale inertia force in terms of characteristic length and characteristic velocity as rho into L square v square, where rho is the density of the fluid, L is the characteristic length and v is the characteristic velocity. Similarly, if we see the viscous force is proportional, can be written as shear stress times the area, surface area on which the shear stress is acting. Okay? Now, the shear stress from the Newton's law of viscosity can be written in terms of the mu into velocity gradient. For a very simple case, it is shear rate, but in a one dimensional flow where u is a function of y only and there is u component of velocity only, then mu into du dy. into the area. So, therefore, the scaling is mu times the velocity gradient. This will be only the velocity gradient. So, mu into velocity gradient. Okay. So, therefore, what you write? Velocity gradient is V is the characteristic dimension, and what is Y? Y is the length dimension L, and what is area? Area is L square. So, this can be expressed in terms of area and the velocity characteristic velocity and length as mu V L. So, therefore, inertia force by viscous force by scaling is proportional to rho L square V square by mu V L, which equals to rho L V by, this is the L we are writing, the same L, why I am writing the big L, same L, rho L V by mu. So, therefore, we see if we have to keep the inertia force by viscous force, this ratio same for both these systems between which the physical similarity is sought, we have to keep the combination of these variables same in both the cases, and the combination of this variable rho L V, rho is the density of the fluid, L is the characteristic dimension, geometrical dimension, V is the characteristic velocity, and mu is the viscosity, is known as Reynolds number. So, in the similar way, we can derive various dimensionless number. Another example I tell you that the problems or process which is governed by both inertia force and gravity force. Now, gravity force is scaled as the mass into acceleration due to gravity, mass into g, and mass is rho L cube g. So, therefore, the gravity force or inertia force by gravity force will be rho L square V square divided by rho L cube g. So, that becomes equal to V square by G L. And therefore, for the problems which are governed by the inertia force and gravity force, their ratio has to be same at all corresponding points between the two systems to maintain that V square by G L has to be kept constant. And this ratio, the square root of this V by root over G L, or sometimes root over G L by V, is known as Froude number. There is no such convention. Sometimes this is defined, sometimes reciprocal of this is also defined as the Froude number. So, therefore, this is known as Froude number, but Reynolds number has a classical convention, it has to be this inertia force by viscous force, not the viscous force by inertia force. So, inertia force by gravity force scale like that. So, this way by scaling the different force, we can find out the similarity parameters which have to be made same for both these systems to maintain the dynamic similarity, that the ratio of the forces at corresponding points will be same. Now, it is not always possible to do this, that the maintaining the similarity we have to always we have to go for scaling of all forces. So, therefore, to make it simple, one can find out the non-dimensional parameters which keep the principle of similarity, make the two systems under physical similar condition by one theorem known as Buckingham's Pi theorem. So, again I tell you, we have seen that to maintain the similarity between two systems, we have to make the ratio of the corresponding geometrical dimension same, the ratio of the corresponding velocities at corresponding points have to be same, ratio of the different forces at corresponding points between the systems have to be same. All these are non-dimensional numbers, and they are usually expressed in terms of the dimensional variables involved in fluid flow, like pressure, velocity, density, the property pressure, velocity, and the property of the fluid, density, viscosity, and the geometrical dimension. For kinematic similarity ratio of velocities and geometrical similarity ratio of physical dimension, it is straightforward, apparent. But for ratio of forces, this has to be done by scaling the forces, and sometimes it becomes difficult. So, a easy method of finding out those non-dimensional numbers which keeps all the similarity has been given by Buckingham and known as Buckingham Pi theorem. Buckingham's Pi theorem. Now, according to this theorem, Buckingham's Pi theorem, one can tell that if a problem is defined by a number of variables, number of physical dimensional variables, let x1, x2, x3, m number of physical variables, number of variables m, number of variables, dimensional variables m. Then Buckingham first, from his intuitive thinking, found that due to dimensional homogeneity, the number of independent non-dimensional terms governing this problem or the process will be less than the number of dimensional counterparts, that is m. M is the number of dimensional variables controlling the process, and the number of non-dimensional variables controlling the process, and all these non-dimensional variables will combine some of the dimensional terms, will be less than that of the dimensional counterparts m. And this was given by Buckingham, and he told if n is the number of non-dimensional variables, independent variables, rather independent variables, you might know number of here also independent variables controlling the problem, number of independent variables, this is known as pi terms, non-dimensional independent. If n is the number of pi terms, then he told that n is the number of pi terms, sorry, here n I will not write, I will write the number of pi terms. Pi terms is the number of non-dimensional independent variables. This will be equal to m minus n, where n is the number of fundamental units, fundamental dimensions, number of fundamental dimensions in which the variables are expressed. Rather, it can be told this way: if a problem is defined by m number of independent dimensional variables, then because of dimensional homogeneity, there will be a less number of non-dimensional variables controlling the process, which is less than the number of the counterpart dimensional variables m. And if these m variables can be expressed in terms of n fundamental dimensions like mass, length, time, temperature, like this, then the number of these non-dimensional independent variables pi will be m minus n, where n is the number of fundamental dimensions in which these m variables can be expressed. Now, this can be worked out. How to find out this number of pi terms? This to find out, we have to do this. Let us consider a problem is first defined by is number of m number of dimensional physical variables. Now, this line of definition of the problem, a problem is defined by this, means here it has to be made 0, implicit functional relationship. Now, first line of this Buckingham's Pi theorem is that we have to write the problem, this mathematical statement of the problem, by an implicit functional relation, where these are the independent dimensional variables governing this process. And what are the pertinent dimensional independent variables governing the process, that you have to know from the physics of the problem or physics of the process. So, after that, if write this thing, if this is the m is the number of variables, m is the number of variables. Now, we see if these variables are expressed by n number of fundamental dimensions, n is the number of fundamental dimensions, then by Buckingham's Pi theorem, the number of pi terms, so pi terms, number of pi terms will be m minus n. Now, how to do it? How to find out this m minus n pi terms? Now, you first select n number of n quantities, n number of quantities as a repeating variable. Let x1, x2 up to xn. That means, repeating variables we these are known as repeating variables. We choose any arbitrarily any n number of physical dimensional variables, any arbitrarily n number, but there should be a caution. In this repeating variable, n number of repeating variables, where n is the number of fundamental dimensions, no variable should be an output parameter of the process. That is number one caution. Number two caution is that all the variables chosen taken together must have all the fundamental dimensions. We should not choose the variables in such a way that in none of the variables one of the fundamental dimension is missing. That means inclusive of all variables, all the fundamental dimensions should be there. And another caution is that no two variables should have the same quantity. That means no two variables should be either geometrical dimensions or velocity. So, these two same physical entity should not be taken. So, if you take so, and you can find out from this the pi term. How? You make each pi term as raise all the repeating variable raised to the power some unknown x n to the power n number of indices, and taking the rest x n plus 1, the rest of the m minus n variables. So, therefore, pi 2 will be formed as x. These ABC sets will be different for different pi term. These sets will be different for different pi terms, and it will include x. Like that, we will be having a m minus n pi term. Pi m minus n will be x1 a, x2 b, x3 c to xn n into x n plus 1 n plus 2 x m. So, therefore, n minus m n plus 1 to m. Okay? So, we say this way we can form the pi terms. Now, all a to n sets are different for different pi term. What we do now, for each pi term, we now replace the dimensional formula of each variables, and indices are there. This is non-dimensional quantity. That means, indices of all fundamental dimensions will be 0. So, if we equate each n fundamental dimension indices to 0, we get n number of equations, and there are n variables. We solve for a to n from all the pi terms. So, therefore, we get the explicit term for this pi term. Okay. So, this way the pi terms can be found out. Let us have an example. Let us consider the principle of similarity in pi flow. Let us consider an example of pi flow problem. A pi flow problem. A pi flow, the fully developed flow in a pipe. Fully developed flow in a pipe. Now, in a fully developed, this is a recapitulation, that is why I am going little fast. Fully developed flow, we can express that the problem as that pressure drop, rather we write this way, you will be able to understand it better, that in a fully developed pipe flow, pressure drop per unit length of the pipe is usually a function of velocity of flow, some characteristic velocity of flow, some characteristic dimensions of the pipe which we call as hydraulic diameter, and the density of the fluid as its property and the viscosity. And this can be expressed as this, a implicit functional relationship of delta P by, this is the output parameter, V, dH, rho, mu, 0. A pipe flow problem is governed by pressure force and viscous force, and a fully developed flow inertia force is 0. So, therefore, delta P by L, V, dH, rho, mu defines as a dimensional variable a pipe flow problem. So, a pipe flow problem can be defined implicitly by this functional relationship. Now, how to find out the, apply the pi theorem? So, here the number of variables are 1, 2, 3, 4, 5. So, number of fundamental dimensions number of fundamental dimensions, that is n, that is number of variables m, n the number of fundamental dimensions is equal to, these are expressed as mass, length and time. All these parameters are expressed in terms of 3 fundamental dimension 3. So, number of pi terms therefore, equal to 5 minus 3 is equal to 2. So, therefore, 2 pi terms. Now, we see that there are number of n is 3. So, we can have 3 repeating variable. This is the output variable, this should not be there. And there are how many choices? There are 4 dimensional variable, choice is 4C3. That means, we can have many sets of repeating variable. One set is V, DH, rho, another set is V, DH, this is comma, mu, another set is DH, rho, mu, another set is V, rho, mu. So, incidentally, all these sets include all the fundamental dimensions. We can take these 3 as repeating variable, we can take these 3, we can take these 3, we can take these 3. Let us take these 3 as the repeating variable, V, DH and rho. And if we take these as the repeating variable, V, DH and rho, then what we have? We have pi 1 is equal to, now we can write here, where pi 1 equals to V, DH, rho we have taken V to the power A, DH to the power B, rho to the power C, V, DH, rho we have taken. So, left parameter is delta P by L and mu. So, first we tell delta P by L and the second pi term we take as V A to the power A, DH B to the power rho to the power C, mu. So, therefore, if we now equate this, pi 1 is what? M to the power 0, L to the power 0, T to the power 0, V is L T to the power minus 1 A, L to the power B, M L to the power minus 3 to the power C. And what is delta P by L? M delta P is the pressure, M L to the M L square, pressure is M L to the power minus 1 T to the power minus 2 and that divided by L, that means M L to the power minus 3 T to the power minus 2. Okay. So, therefore, delta P is M L to the power minus 1 divided by L, M L to the power minus 2, sorry, M L to the power minus 2. What is delta P? Delta P is the pressure, that is M L to the power minus 1 T to the power, okay, then divided by L. So, therefore, if we now equate the L, M and T indices, we will get here A is equal to minus 2. If you do it, B is equal to 1 and C is equal to minus 1. If you equate L, A plus B minus 3C is equal to 0. Similarly, for T, minus A minus 2 is equal to 0, A is equal to minus 2. This way you get this. And if you do the similar procedure for this thing, that pi 2 M0 L0 T0 is the similar procedure that L T to the power minus 1 to the power A, L to the power B, M L to the power minus 3 C and mu is the M L to the power minus 1 T to the power minus 1. Then you get this. In the second situation, A is equal to minus 1, B is equal to minus 1 and C is equal to minus 1. And if you put this in the pi term, the value of A, B, C, you get pi 1 as delta P by L, that is the pi 1 as you get dH by rho V square, and pi 2 if you put this, you get pi 2 is equal to mu by rho V dH. Okay. So, this you get pi, if you put the value of A, B, C here, and this you get as pi 2 if you put A, B, C value here. So, pi 1 will be delta p by L dH rho by V square and pi 2 will be mu by rho b dH. Thank you.